Okay, so is it starting?
Yeah.
Okay. So now that I have gotten through the boring part, we've already defined what is a quotient space. I will now just repeat the definition real briefly. V quotient W is the set of cosets x plus W such that x is an element of V. So basically here the idea is, so x plus W, yes, is a set of things, but we often use the notation x plus W is equal to bracket x like that. It's just, it's convenient for the purpose of the examples that follow. I'm not sure it's the best thing, but let me show you some actual examples here. So let's take V, for example, to be R3, and I'll take W to be the set, let's say here, how about x comma y comma 0, such that x and y are real numbers. Okay, so I can draw a picture of what's going on here, right? I can actually draw a picture of what this looks like. So we know what R3 is, right? What's W actually?
An XY plane?
Yeah, it's the XY plane, right? So basically W is itself this guy, let's say, right? And so if I were to pick another coset, let's say, I'll draw it up here. And I'm just drawing it as if it's in the first quadrant, but of course there's more than that, right?
Mm-hmm.
This, for example, might be, let's say, we could do 0, 0, 1 plus W, but that would, 0, 0, 1 would be this point right here, but you could pick any other representative for that coset. Like it would be the same if I just say, like out here, that point would be 1, 1, 1. And these are equal as point sets. They're both just the horizontal plane at z equals to 1, right? So in the easier notation, I would just denote this by the coset with representative 0, 0, 1. Notice the brackets, and I'm saying that that's in fact equal to 1, 1, 1. To check on that, notice that the difference of the representatives, what is it?
1, 1, 0.
Right, which is an element of
W.
W. So there you go. That's going back to proposition 1 from last time. Right. Also, in terms of just three-dimensional coordinate geometry, that's because we're taking the difference of points in a plane and we get a vector in the plane. But okay, that's one. There's a picture of the subspace, a coset, and we can picture another one while I'm at it here. All right, so another coset would be something like, well, suppose I took and added this to itself, right? So for example, 0, 0, 1 plus 0, 0, 1, like add the coset. What would you get? You get 0, 0, 2 plus W. I'm bouncing back and forth between these two different notations, but geometrically, if you add this plane to itself, you get this guy up here, right? So there you go. There's 0, 0, 2 equivalence class. The coset represented by 0, 0, 2. And again, that's not unique. I could pick any other point in this horizontal plane. It would also be a representative. So you see what we're getting is this like stack of planes, right? Every point in R3 falls in just one of these planes, and these planes partition R3 into a stack of planes, right? And the coset space is basically saying, think of the planes as points, then you can add planes, right? You can add two planes together and you can get another plane, and that actually has a vector space structure. That's the quotient space. Okay, so there's one example. Now, what would happen if I instead took W equal to, say, x0, 0? What would the difference there be? suppose I do that instead. Then what is the
The line.
yeah, that's a line, right? What kind of line is it?
On the x-axis.
On the what?
X plane.
Yeah, right. It's in the right along the x-axis. It'd be a line, right? Let's see here. So, if I look at, say, let's see here. Trying to think. If I had, oh, all of a sudden I'm lost for words. Oh, let's see here. So what would it look like if I had, oh, right. So if I had x1, y1, z1 plus w equal to x2, y2, z2 plus x2, y2, z2. So if I have two different representatives for a coset here, what you know, I don't really need x1, xy1, x1, y1, z1, and x2, y2, z2, right? Like we can, in the previous example, if you really look at it, all I needed to know was the z-intercept, right? And that was a unique label for each one of the cosets. You know, so I didn't really need a three-dimensional vector to label the cosets. I could just label it by its z-coordinate if I wanted to. So I'm trying to discover here what's like a unique, how to label the cosets here. So if I look at the difference of these, what do I get? So like x2 minus x1, y2 minus y1, z2 minus z1, right? That has to be an element of w, right? And what does that mean? That means that this is what?
0.
0. This is 0. This guy's free. So you see then that we have to have that y1 is equal to y2, and we also have that z1 is equal to z2, right? If these are the same coset. Now let's see if I can think about it. I don't know. I'm a little bit worried about the picture here, right? Not sure I can think of it right offhand, man. All right, so here's x, here's y, here's z. What is 0? What's the 0 coset? It's what? I think you knew it, Sharon, at the start. It's just the line along the x-axis, right? That's so there's 0, 0, 0 plus w, right? Or you could label it basically. You could say 0, 0, 0, right?
Mm-hmm.
X is free though. You could just as well say x 0, 0 for any x, and you'd still have the same point. But I guess what I'm trying to get at here is the y and the z components label which coset you're looking at, right? So another coset here would be something like, let's see here. Colors. How about geometrically, what would this one be if I did foolishly attempt to do, I don't really care what x is, I'll put a 0 here, it doesn't really matter, but more to the point, let's put y equals to 0 and z equals to 1, right? So, I mean, you can think about this geometrically, so basically I'm just saying, go up 1 unit along the z-axis here, right? And then add w. Well, w is this purple line, so that gives you, parallel line like that. And so if I was to draw this a little bit differently, if I was just to draw it kind of as here's the y and here's the z, then my 0 is right here, right? And other things just appear as points, right? Like in terms of perspective. So I've got whatever I want for x. I'll let it be 0, but it could be whatever. And the point is, that y and z, I mean, that is actually fine. If I do b and c, there you go. I mean, that would be at y equals to b and z equals to c, and it's that line coming out of the board and into the board if you want to think about it three-dimensionally. So in this quotient space, the points are actually lines if you look at the underlying sets. So quotient spaces in R3, you either have a quotient by, you know, interesting quotients, I suppose, either by a plane or by a line, right? What happens if you take all of R3 and you form the quotient by that? Well, that's kind of silly. We'll talk more about this after the break probably, but for what it's worth, if you take R3 and you mod by R3 itself, you just get the 0 subspace. And if you take R3 and you quotient by the 0 space, well, guess what? You just get back R3, so... Well, I should say isomorphically, but anyway. Okay, so there's a couple of geometric examples. Maybe that helps. I don't know. Maybe not. Let me go on here. Is there any questions? You know, this organic board cleaner, it's questionable at best.
Not like Expo.
Expo is so much better than this junk. I don't know, for some reason the order from Staples for the department and not Expo, so. Chinese Sharon has arrived.
What? Chinese Sharon? How dare you?
Hey,
I'm the more
that's
dumb.
mean to Sharon. Okay, so so we can also look at more abstract
They cannot
quotients.
see me, right?
More abstract quotients. For example, here's one I like. Suppose you have nth order polynomials. So that would be what, like an x to the n plus an minus 1 x to the n minus 1 plus da 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 plus a1x plus a naught, such that, you know, a naught through an are real numbers. That's my vector space, all right? There's, I think, perhaps the most interesting quotient space to look at here, in my opinion, is to let W just be the set of constant polynomials. So let W equal to just, you know, a naught, basically, such that a naught is a real number. I mean, you can see all that is just basically, you can identify it with the reals. I mean, technically it's a set of constant polynomials, but one-to-one correspondence between that and reals and real numbers. And then I can look at the quotient of Pn by W, right? Like, what does that look like? So let's suppose that we have f of x and g of x in this quotient, right? What does that mean? And let's also suppose that f of x, the quotient, the coset of f of x, is equal to the coset of g of x. What does that say about f of x and g of x? So you remember we learned that's if and only if f of x minus g of x is what?
Is an element of W?
Element of W, right? Which in this current context is to say that f of x minus g of x is equal to a constant. So in this quotient, basically, this is a way of, in this quotient space, it's a formal construction that allows you to say, basically, functions that differ by a constant are are really the same thing.
Okay.
So this is actually very interesting, right? Because one of the problems we confronted earlier was differentiation, right? So if I look at the differentiation operator, say from Pn to, let's say, Pn, where we had d f of x defined to be what? Just, you know, df dx, right? We noticed that if you have d of a constant, you get d dx of a constant, right? And that's 0, right? That's all that's there. So, in other words, the kernel of D, it's actually equal to, what is it equal to? Well, it's equal to constant polynomials, right? Well, I mean, in particular, I have a name for that at the moment. The kernel of D is exactly W. It's a set of constant polynomials. And that's, I mean, the derivative fails to be one-to-one because of constant polynomials. Right? Two derivatives can be the same and yet not come from the same function. However, if I was to define, let's say, d bar on the quotient of polynomials by W, right? Let's say to, I don't know what do I want to say to? I guess we can just say Pn. And define this by d bar of the equivalence class of f of x, right? What is it going to be equal to? Just equal to, say, df dx, right? So that takes in a quotient, a coset, an equivalence class, really, of functions which differ just by a constant, and I just differentiate them. And then all of a sudden, what's the kernel of d bar? Well, the kernel of d bar, it's
No.
it's the constant functions, right? It's the coset of the constant functions. So it's this, which is W, right? Which is, by the way, the 0 in the quotient space, right? That is the 0 in the quotient space, right? So therefore, the derivative operator is one-to-one on this quotient space. So this gives us, basically we're seeing that if we modify the domain, right, if the reason that something is failing to be one-to-one is because you've got, this degeneracy, like all these different points which are mapping to the same point, well, if I just take all of those different points which are mapping to the same point and I say, hey, those different points are really just elements of a common coset, then all of a sudden, if I look at the quotient space formed by squashing those points to the same coset, then I get a one-to-one mapping. So this actually allows me to give a careful statement in which I can actually argue that the derivative and the integral are honest-to-goodness inverse operators. If I think about coset, if I think about quotient spaces in the right way, I can say that. Now, that's one example. One more example, and then I'll state the big theorem, and we'll be done. So the other, I tell you. Oh well. Other example I'm fond of is, well, I tried. You could look at V equal to Rn by n, and let W equal symmetric matrices. So A such that A transpose is equal to A. Okay.
See what I mean about
This would give you another kind of quotient space. I don't want to say too much about it, but there's another. You could do that. So like, let's see here, something like, goodness gracious, how to say this? What would the representative of the coset here look like? So if I had, say, A1 plus W equal to A2 plus W, and I really wanted to pin down how do you label the coset, right? What if A1 and A2 is essential to saying which one's which, right? It's exactly the part which is not in W. So that's true if and only if what? A2 minus A1 is equal to 0, right? Not 0, excuse me.
What W?
Stooge. Yeah, an element of W, right? And what's that mean? A2 minus A1
Plus
transpose is equal to,
A2 minus A1.
right. So, I don't know, I'm not getting a lot of insight into that real quick here. I'm going to stop talking about this, but that's another example you could look at and try to flesh out. It's more interesting to actually look at this example as it pertains to the application of the next theorem, so I'm going to just go ahead and state the theorem and go on with it. I tell you.
Gotta save the planet.
Keep your planet. Okay, so I just showed you how we can basically modify the domain of a mapping and make it into an injection. So it turns out that we can do that in general. So here's the theorem. If T is a linear transformation from V to W, V and W vector spaces, okay, then there exists, let's say, T bar, a mapping from V mod the kernel of T to the image of T. So that's the range. We called that the range of T earlier today, or whenever you watched the last one. I don't know. So there exists this T bar, and T bar is an isomorphism. Meaning what? T bar is 1 to 1 and onto. Let's see here. I think I can be a little bit more more explicit about it. T bar. How do we actually construct this T bar? So T bar is a mapping from the kernel, from V mod the kernel of T, right? So I typically would look at something like X plus kernel T. And what would my definition be for this function?
It'll be a transformation.
I mean, you got to give me a formula here. All you got to work with is T.
So.
There's really only one thing to write down at this point.
V to W?
T. I'm looking for a formula here. T of what?
T of X.
Right, T of X. Yeah, that's all that you can do. I mean, we have T. T eats things from W. X is from T. X is from V. T of X makes sense. All right. The question then is this a well-defined mapping, right? Because we just defined it on a coset. The representative X is not unique. So what would happen if we took a different representative?
Get T of X?
Right, that would be T of X prime. And so I'm going to assume what? To make this interesting, I'm assuming that X plus the kernel of T is equal to X prime plus the kernel of T prime, kernel of T rather. So same coset, different representatives possibly. These are equal. What is that? Well, okay. Now for this to actually, for T bar to actually be a function, goodness gracious, I'm going to be in trouble if T of X and T of X prime are actually different values, right? Because then T bar wouldn't be single valued, we'd be in trouble. So consider though, the difference of T of X and T of X prime. What's that say? That's T of, using additivity and homogeneity, we get X minus X prime, right? But what did we know about X minus X prime though, by the way?
It needs to be 0.
And we know that because up here, X minus X prime has to be an element of the kernel of T, right? Which means that T of X minus X prime, as you said, is 0. So 0, hence T bar so defined you know, as in this is the definition, is single valued. We've shown it's a function. It remains to show what? I said it's an isomorphism.
It's an isomorphism.
So we need three things, right? We need to show.
It's 1-to-1 onto
Mm-hmm.
and something else.
Remains to show. More basic, right? T bar linear. We need to show it's linear. And then yeah, T bar 1-to-1. T bar onto. So how can we show T bar is linear? Well, let's just do it. T bar of x plus kernel T plus y plus kernel T is equal to what?
X.
T bar of
X plus y.
yeah, x plus y plus kernel T, right? By definition of the addition there. And that's what? That's T of xy, right? X plus y. By definition of T bar, but by additivity of T, that's T of x plus T of y. But by definition of T bar, that's T bar of x plus kernel T. I'm starting to wish I'd used the other notation. T of x y plus kernel T, yeah. Hence, T bar is additive. And the proof of homogeneity is as simple as slapping a C here, 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 here. Oops. Yeah, there, and there. Yay! I'll say it's homogeneous. Now let's show why it's onto. Why is it onto? So to show something's onto, we should pick something in the alleged, the codomain. So
show that it exists.
right. So let's let Z be an element of T of V, right? Then by definition, Z is equal to what? It's equal to T of something, right? I mean, the codomain is T of V, so I mean that's the image of T under V. It's got to be some X or V, or I'll use X, okay? So how do I show that T bar maps to that? No, this is like really low-hanging fruit, right? T bar of blank, let me make a little slightly bigger blank, is equal to T of X. It's equal to Z, hence T is surjective. T bar is surjection. So what do I put in the blank?
X plus kernel T.
Exactly. See? You want this for a test question. You already know the answer. It's good. So it's easy to show it's 1-to-1, which, onto the surjection. Now how do we show it's 1-to-1?
That the function equals.
Let's calculate the kernel of T bar. If we can calculate the kernel of T bar and show that it's just 0, that shows it's injective. So that was the theorem we had. So kernel T bar would be what? It's x plus kernel T, such that what? T bar of x plus kernel T equals to 0, right? Now that's 0 in the quotient, right? So that's actually 0 plus kernel T, right? Oh, excuse me, that's 0 in the image. That's actually just 0 in V, sorry. Excuse me, 0 in W. This is a subset of W, right? We take subspace action, technically. All right. Anyway, so what is that? So if we focus on this here, what do we got? We've got T of X, right, equals to 0 by definition of T bar. What's it say about X, though? X is an element of the kernel of T, right? Which then tells me that X plus kernel T is equal to what?
Zero?
0, but I mean, there are different ways we could go with it. It's equal to the kernel of T again, right? Which is, by the way, the 0 in V mod the kernel of T, right? So the point is, yes, the kernel is just the 0 in the domain, therefore the function's 1-to-1. This theorem that we've just stated up here is known as the first isomorphism theorem. Can't spell morphism theorem. So, second here, I'll tell you if I have any interesting examples. I think, well, so the, let's see here, for me, I thought the interesting example was the, I'll just do one example and then we'll be done. The, so I can erase. So for example, if we look at that, we look at a map from, I want to look at a map where the symmetric matrices are the, let's say the kernel of the map. Well, I don't know, I forget, but there's two maps to make. So let's say if it was T of A is equal to A, I'll do A minus A transpose. I forget what I did in the notes. I may accidentally do a homework problem here. If I do, my apologies. So here T is a mapping from n by n matrices to n by n matrices, okay? What's the kernel of T? Right? So that's A such that T of A is 0, but that's exactly A such that A transpose is equal to A, right? So this, in other words, the kernel is symmetric matrices. Right, what's the image? What's the image of, what's T of Rn by n? So we're basically looking at, you know, A minus A transpose such that A is a matrix. What can you say about, if I call that thing B, what can you say about B? What is, you know, do we already have a name for these kinds of, I mean, besides just saying it's the image of T, does it have another name? Well, check it out. What's B transpose is what? Excuse me, B. One thing at a time. B is equal to A minus A transpose. So what's B transpose equal to?
Oh, A transpose minus A.
Right. Which is minus A transpose, right? AKA minus B, right? So what we have here is the set of anti-symmetric matrices. That's the image of this map. First isomorphism theorem tells us the following. It tells us if I look at the set of n by n matrices and I quotient by the set of symmetric matrices, what I'm left with, that quotient space, is isomorphic to the set of anti-symmetric you know, n by n matrices. And the isomorphism, what provides that isomorphism is this T-bar mapping we've been talking about. So, and then what we're going to talk about after break, the next section, Monday, we talk about is so-called direct sum decomposition. We're going to show that this goes hand in hand with this curious statement that our n by n is equal to, let's say, the symmetric matrices direct summed with the anti-symmetric matrices And if you have a direct sum decomposition, if you take the quotient by one of these things, you're just left with the other thing. When you have two things. It's more complicated when there are more things being added together. Of course, we don't know what this funny symbol means yet, but I guess you could read ahead and find out. I will shut up about it for now, but that's where we pick up Monday. Like 10 days from now, whenever it is. Thanks. That's all I got.